Hello, good morning, everyone. First, I would like to thank you for the opportunity to share my study. My name is Angela. I am a PhD student at the Federal University of São Carlos, São Paulo, Brazil. And today I will present a part of the exploratory phase of my studies about heat islands in industrial zones. This article was written with my advisor, Érico Maciero, and it's titled Analysis of the Correlation Between the Formation of Urban Heat Islands and Surface Temperature from Simulations and Thermal Imaging in Industrial Zones. Urban heat islands are phenomena resulting from the difference in heat between urban and rural areas, resulting from the interaction of several factors such as density of buildings, building materials of great energy potential, absence of vegetation cover, and anthropogenic heat. The high concentration of buildings, intense traffic, and anthropogenic waste heat resulting from industrial areas have been recognized as contributing factors to formation of the urban heat islands. The industrialization process of Brazilian cities occurred in a vertiginous and intense way, especially in the city of São Carlos, Brazil. In order to contribute to the studies of thermal comfort and urban climate, some numerical computation and infrared thermographic analysis models are used in open space. In this case, we use the InfMed software, which provides results for properties such as temperature, relative humidity, surface temperature, solar radiation, wind speed and direction, surface albedo, among others. Urban heat island simulation help to understand how these phenomena occur and also to estimate the effectiveness of possible mitigating measures. To obtain surface temperature in cities for large areas is difficult. The measurement is performed through remote sensing using satellites, aircraft, or aerial vehicle unmanned (UAV). The main limitation of these methods is that the camera is obstructed by urban geometry and the surface temperature can be not accurately captured. The method consists of computer simulation using InMed software to obtain air temperature and surface temperature. To analyze the correlation between air temperature and surface temperature and verify the behavior of urban heat islands, thermal simulation of areas for 24 hours, and the collection of thermal images of urban surface at different times, 10 a.m., 3 p.m., and 10 p.m. of typical day using a thermographic camera coupled to UAV. At the end, the simulated and measured data were compared to those obtained by the formula proposed by Younger for areas with a radius up to 200 meters to verify correlation between air temperature and surface temperature and verify the occurrence of urban heat islands in industrial areas. The development of the method of this research was divided into following steps. Characterization of three areas: urban areas and industrial zone in São Carlos, compare simulation of urban areas with industrial occupation through the InvMed software. The collection of thermal images was performed at 3 times using a FLIR 1 Pro thermal camera coupled to a UAV. Comparison of the results and relationships between air temperature and surface temperature proposed by Unger et al. Using simulate data obtained through thermal images and data of the National Institute of Meteorology. The city of São Carlos is in the interior of the state of São Paulo. The climate is humid subtropical, altitude of 856 meters. This figure show the study areas, area 1, 2, 3, and the receptors study in InvMed. And this another figure at the right shows the path of the UAV and terminal camera. The simulation using InvMed took place on July 2021, a clear and a calm day without precipitation, lasting 24 hours. The input data for the simulation were obtained from a meteorological station located on the campus of the Federal University of São Carlos, 7 kilometers for the industrial district. The urban heat island intensity was calculated through the difference between urban and rural air area. The images were obtained using FLIR portable thermographic camera embedded in UAV 120 meters above the surface on the same simulate date. The thermal images from the scenes was acquired in different times, 10 a.m., 3 p.m., and 10 p.m. Let's talk about the results and discussion. This figure shows the physical composition of each area: roof, vegetation, asphalt, and soil. The area 1 and 2 have approximately the same percent of waterproof surface, 41%, but the area 2 has an area covered by vegetation, 58% greater than area 1. The highest intensity of urban heat island record was for B2 receptor and the area 1, reaching 6.8 degrees at 10 p.m. as shown in this figure. Area 1 had a higher intensity of the urban heat islands due mainly to the characteristics of low index vegetation, higher heights of impervious surface, and exposed soil. The wide use of concrete or metal surface can reduce the total urban thermal emissivity, implying an increase in the levels of net urban radiation. Vegetation plays a crucial role in cooling the environment and decreasing air temperature since close to vegetation, air humidity is higher, favoring evaporative cooling and increasing the flow of latent heat. In a research developed for the month of April 2021, 14. Thermal differences were found in the range of 5 to 7.2 degrees through a mobile night transact in the city of São Carlos. The maximum thermal difference recorded by these researchers of 7.2 degrees was recorded at 7 p.m. in areas of popular residential neighborhoods and commercial and service areas with a greater flow of people and vehicles and density built. This figure shows the surface temperature near receptor B1 at the 10 a.m., 3 p.m., 10 p.m. These images was obtained with the thermal camera. The maximum variation was 23.3 degrees. Looking the surface temperature obtained by simulation at 3 p.m. and 10 p.m., we saw the peak, the maximum variation was 13 degrees, and the peak time of for the air temperature coincides with the maximum surface temperature at 3 p.m. This figure shows the correlation between air temperature and surface temperature. All the results of this research are presented in estimates according to equation 1 proposed by Unger. Both the correlation for the measured and simulated results remain below the stipulated by Unger in yellow, as we see. The highest correlation coefficient 0.79 was found for that data measured through the thermal photos, following by simulated results. A better correlation could be obtained using apparatus during the collection of photos, aiming to reduce interference for infrared radiation and collecting of the air temperature. Considering that the industrial districts occupy vast areas, this work presents an advance in the study of correlation of surface temperature and air temperature in industrial areas, providing an equation that correlates such parameters using accessible equipment, portable thermograph camera, and microclimate simulation software, and also demonstrating the possibility of the study of urban heat islands from such a correlation. The study of the microclimate present in the urban industrial zones is of paramount importance for understanding of and mitigation of urban heat islands. In this study, it was possible to establish a correlation between air temperature and surface temperature in this area based on simulated and measured data previously presented for urban centers and peripheries. Such correlation is an advance in the study of urban heat islands formation in industrial areas because provides one equation that correlates the two parameters, use affordable equipment, and portable thermographic camera and microclimate simulation software, and it also contribute to understanding of the physical phenomena of heat exchange between surface and atmosphere. The highest intensity of the urban heat islands was found in the Area 1, with the lowest proportion of vegetation and the highest rate of the waterproof area, reaching 6.8 degrees at 10 p.m. That's all, folks. Thank you for your patience.